Okay, let's start. I think we stop where we stop. We stop it a little bit there to explain the dimension of the matrix LOVCs. Is it? Okay. So we have, maybe I presented you this, that there are different kind of sequence modeling task, many to one, one to many, many to many, many to many. I explained yesterday with some example, and I will be back later on. So now we will see how to train our recurrent neural network. So this is the goal, just first goal, how to train it. So the training, you know what you do in neural network framework. Mainly we use backpropagation, and you need to do all the backpropagation step process, and this will be through the time. So we will see just now, a little bit technical, but it's good to see it once. I put maybe like this is better. Yes. Oh, okay, better. So the RNN have nice features, we say. Can process any length input, and in theory, for each time t, can use information from many steps back. But we see some trouble maybe. And we have the same weight applied at every time step. Okay, but we see that the RNN could be very slow to train. And in practice, it is difficult to access information from long, many steps back. So this is a trouble, and we see how to deal with this. So to train our recurrent neural network, if I take the same example of the model, the language model example, so assume that you have access to a big corpus of text, and you have a sequence of a lot of words, so denoted by x1 until xt, okay? So you have a lot of words. So if you do the forward pass, and you have to compute the output at every time t, okay? So this is you, okay, if I put a neural network, a recurrent neural network like this, you have the input at time x t minus 1, there you have x t, go there, and you have the output there, and you have the output there. And to get the output, in fact, is you use a softmax, and it gives you a probability to be to the highest, and you get the word we have the highest probability. So this can be a little bit, if you have a long corpus, it could be long also, and you have to compute the loss function at each time t. So the loss function, what we use here is the cross entropy between the predicted probability at each time t and the true next word. And so remember that we have the one out for xt plus 1. So the cross entropy, your loss function here, I put theta, but I could put a w for the parameter. So the cross entropy, remember, for categorical variable, so is like this. This makes sense for everyone, this cross entropy? So in our recurrent network, we need to compute the cross entropy, but you can see that the loss is at each time t. This is the main point. So as you have, sorry, and you need to do this loss function to combine all the loss at each time t. So you take the average over all your words, all the corpus. Okay, and so you have seen that the cross entropy is getting this double sum. So computing the loss, is quite expensive, and you have to compute the gradient across entire corpus. So of course you will not do this, and you will do like a batch, like a mini batch. So the batch, it will use as a batch of sentence to compute the loss. Okay, so a small chunk of data, as we have already done in the for the over architecture of neural network, like the fully connecting neural network or the CNN. Okay, I just put the chat because it might be some question. Notation. Okay, sorry, I didn't see the chat. A question from Len, and nobody replied, so I need to reply. Just wanted to clarify the notation in the why the output of the output layer. Okay, good point. So we have two things. I think I explained here, but Len, I will try to clarify your point with a picture. When you are there, here, Len, you get it? Is the notation, in fact, this with this word, you want to predict, in fact, the next word. Okay, is maybe the bad notation, but the diagram, yes. So with this, the output of this with the W, you will compute the softmax, and you will get a Y hat at T minus 1. Okay, and so this Y hat, sorry, here, Y hat is there, and you compare to the desired one. The desired one is the next word. So in fact, this one should be, you can see this like xt. It makes sense? Should thus y as hat. No, because it could, it depends on how you explain because you have the real y, the desired y. Makes sense, Christina? And okay, so it's like, for example, let's say, oh, AMZ, I will say an example. AMZ course is great. Okay, this is my sentence. So this is x1. When you have x1, in fact, you want to predict the next one. Yep. And so on and so on. Is clear for everyone? The y hat and the y? Yep, thank you. I hope the thank you was for this. Okay, I keep going, so? Okay, so it was good to clarify this. So now everybody know what is in my loss function, eh? This and this one. Okay, the difference. Okay, so now I'm back to what? Yes, so we want to understand what is the back propagation through time. So this is important, is our goal. So you have your loss function. You get it, the loss function? So the loss function is the sum of the loss function for each time step. Make sense? So, and this has two summation of this loss function, because there are you have for all the loss. So the first summation is over all L, so all the loss. And the second summation is over on the weight matrix. So in fact, if I will be more clear, you have this loss function, and we want to get, for doing the stochastic gradient descent, you want to compute this. So now with this computational graph, you can see what I'm saying. The two sum is the first sum is over the L, and when you are in 1L loss, if you go to the back propagation is going there and is going there, and you have all this. So you have a sum over all the W. Makes sense? Or for example, for LT plus 1, you have this pass, and you have this pass, and this pass, and you have this pass, and this pass. So now we need to do this, and to apply the backpropagation step is chain rule. Okay, so first one, if I try to do the derivative in respect to W, the matrix HH, so I will have the first sum over all the time t, and I have the derivative of each one. And now if I need to derive one specific loss function for time t in respect to W, I have this sum because this time t depends of all the previous time. So you get this sum, so all this previous time, from time 1 until time t. No reaction, so it should be good. So now, how to compute this? I will focus on this derivative. So it's a partial derivative of my loss function at time t in respect to WHH, and just apply the chain rules. So the first sum, you can get the first sum. I decompose is the derivative in respect to the prediction at time t. And after is the prediction at time t derivative in respect to the hidden state at time t, so ht, and ht is depend of what is the path, depending of hk, and hk depending of w. So we applied, in fact, what we have to compute. You can see that now we need to focus on this part. So, because you can see that this sum here is depending on the index k, so we can go this sum through there. That's my point, because all of this part doesn't depend, it's still there, but doesn't depend of k. Okay, so now we need to compute the derivative of h at time t in respect to h at time k. And so if you apply the chain rule of differentiation between this time window from k to t, what you have is you have the product from k plus 1 until t of all these derivatives. Okay, so now, do you remember what is the correspondence to our, what is our, sorry, I list. Yeah, okay. I just wanted to check the chat, so all is good. And what I wanted to tell you is what is the relation between h. So remember that our model to compute this derivative is that we know that h t is equal to function of what we have, WHH multiplied by h I would say t minus 1, yep, plus whx multiplied by x time t. So this is our key relation in our recurrent neural network. Okay, so if now I need to compute the derivative at hj respect to hj minus 1, I still got this product, and you can see that this whh, you just do the derivative, so it's a chain also again. So you have the f derivative, and after you have this wh, and this is a diagonal, in fact, because this is a matrix, is a diagonal of x. So this is your solution of your chain rules, and you can see that this guy here, which is so this is a vector, this is a vector, so this is each guy is a Jacobian matrix, and I put the Jacobian matrix here, and I think it's some error in the website. So anyway, so you have this. We managed to compute the derivative of our loss function using the backpropagation over time. Oh, I put here, sorry. Ah, yes. And so now, what is the issue with the RNN? So the RNN is well known to have a vanishing and exploding gradient problem. So I remind you that the relation, our key relation in the RNN is this key relation. So now, just to get the intuition about this, consider that the activation function using is identity. It's just to simplify the derivation. So now this derivative is as the diagonal, it was before it was f derivative, so now is identity, so I will have the identity matrix, and in fact this guy is just the matrix W, where we have our weight. So now if this is for two consecutive time, so t and t minus 1, so now consider that you have you want to compute your loss function in respect to at a time I, in respect to h at time j. So if you're doing this, and by applying the chain rules and with this relation, you end up by the derivative of L I in respect to I, and with this product. And this product is, we have just seen in this simple example, but is WHH. It's a little bit technical. Okay, I got it. And so you have WHH, and you have this L time, because this produce is from T going to J to I. So if the product is going to J to I, we have L element. So in fact, is end up that this derivative of the loss function at time J, at time I, in respect to Hj, is going by this guy. All good? Let me see. But I hope you have read before the chapter. Huh? So, what is our issue about our gradient descent? So think about that WHH is small. So if H is WHH is small, as you put the power of L, this will be going through where? Going up or down? So L, remember L is the time lag between two long time steps. So if L is far away, is a big, huge, I bet WHH will be very, very small. So if I formalize it a bit more, if you consider that WHH is diagonalizable matrices, you can decompose this matrix between three matrices, Q minus 1 multiplied by delta multiplied by Q, and Q is the eigenvector, and delta is diagonal with the eigenvalues. So you know this by simple algebra. So if you want to compute the power of WHH, because we want to compute the product of the power of WHH, and if you compute this, is easy doing by this equation. And so if you have some eigenvalues lower than 1, it will lead to a vanishing gradient. But if you have eigenvalue greater than 1, you will have an exploding gradient. So this coming from this L, and the way R is computing the derivative, the gradient. I hope you get an intuition about this. Can I have a yes or no or lost? It's bad because it's my last lecture. Okay, thanks. Okay, so it's okay. So some conclusion. Oh, is it my, oh, it's not my lecture. 8:21. Oh, it's very weird. I don't know, okay. Anyway, so some conclusion about this. Gradient signal from far away is lost because we can see that it's much smaller than gradient signal from close by. So if you are far away, your gradient signal will be lost. So weight are updating only with respect to near effect. So we have a problem of not long-term effect. So we will be a trouble in the language modeling, and we will see how to overcome this issue. So you can see that the gradient, I say it can be viewed as a measure of the effect on the past on the future. So if the gradient is small, is the meaning that you cannot learn this dependency, and the model is unable to predict similar long distance dependency. So this is a problem of vanishing the gradient. And the exploding gradient is can be also a big issue for updating the weight, and you can even have some overflow. Okay, so be careful of this. So a way to deal with this is, I think Sarat explained this maybe to the exploding gradient, or I explained before, is a gradient clipping. Do you know what is a gradient clipping? I don't know if you pronounce clipping or yes, gradient clipping. You explained this, Sarat, the gradient clipping?
No, Benoit, I didn't explain.
Okay, so it's just the gradient, to scale the gradient at when the gradient is greater than, you take the norm of the gradient, and if the gradient is greater than a threshold, a given threshold, you scale the gradient to the threshold. So this is a way to not have an exploding gradient. So this, I can give you some paper more about this. Okay, so a short summary, advantage of the RNN. Advantage, processing input at any length. So this is an advantage of RNN. Model size is not increasing with the size of the input because the weight are the same. dimension of your model. The computation takes into account historical information due to the recurrent rules. The weights are shared across time, so it's the same weight using across time. So this is great, all this good advantage. Drawback, we have seen computation could be very slow. And the main is difficulty to us to get information from a long time ago. Okay, so just to finish, I have some question about for you. Okay, so some example of different architecture of the recurrent neural network. Yes, no. What is a no, Alex? Ah, yes, the clipping, sorry. Can you, what is about the question mark? So this is called one-to-many. I think I've done a recap like this because I prepare, it's like a warm-up for your quiz this weekend. So what is the Tx? What is the value of Tx? Yeah. Remember, quiz, you need to be fast. Then good. One, perfect. And this is useful for is an application is a music generation is using this kind of architecture. You just one input and is doing the flow for the music. Another, which is called many to one. So many X, one prediction. Application sentiment classification. Okay, TX. I need to put how many TX? Greater than one. Perfect. TY. TY one. Good. Go fast. Good. Okay, and so very bad. I don't know if I have a good slide. Oh my god. This one. Many too many. Many too many. Yes, this is a good point. What I wanted is Tx equal Ty equal to 1. So same number of input at output. And you have, for example, also, this is also called a many to many. What's about this one? Yes. So the point here is Tx and Ty is greater than 1, but Tx, yes, is different of Ty. Okay, machine translation. A sentence in French, maybe you will translate in English with more words or the reverse. Okay, good. So overview of the RNN, we present the RNN like this. So this is a general representation of the RNN, but we have also some variant of the RNN. I don't know if I told you about this. Is the BRNN. So the BRNN is for bidirectional RNN. So what is the way of the bidirectional is that you learn in one direction, but you learn is also in other direction. The question of Len. Could we everybody help Len to reply? In the last many-to-many architecture, must the input enter before any output is producing? Yes. It's first the input and after the output. Right. The machine translation is like this. The simple machine translation. We will see as later with encoder decoder. Okay, so for this one, you get this one is going in one direction, in another direction. I can give, okay, this say is popular in speech recognition, but if, for example, if I say I am, and I need to find what it is, so it's my task. Okay, I can do a recurrent network. is the same as this one, is the initial state. It's like, because you know, in neural network is a recurrence, so you need to have H0. Before it was calling H, but this is A for the activation at time 0. Okay, so my task is I am, okay, and the recurrent network try to deal with this. But if I have more, if I want to still to know what is this miss word, and I would say an example, hungry. Hungry. It's true, I am hungry. I am hungry. And I can have also have a sentence longer. So I am hungry, and I can eat half what I like, kangaroo, because I like kangaroo. So what do you think? It could be the first part. You have maybe the response is happy. I am happy because I teach you. But if you have the last part of the sentence, or I say hungry, you will think maybe I am not hungry. But by using all the information from the end of the sentence, you will maybe say, I am very. So the idea of the bidirectional is to take some information for the beginning and also from the reverse side. Make sense? So this is a kind of architecture also, the BRNN, which is very useful. You got it? Okay, my point is that there, the RNN is can be seen as a gate. And I changed a bit the notation because I still have this nice picture. So we recognize that our recurrence is there, our recurrence, with my new notation. Yes, exactly. Yes, now we put on this side and on this side. We fit it in the two way. So this is a representation of our RNN with a gate. So you have your input, you have what we want to predict, and you have a function which is generally the sigmoid or the tan or whatever, and you have the function, activation function, for your prediction, which is generally in language processing a softmax. Okay? And you can see in the gate to represent that we represent our relation. So you have the multiplication with this weight, and after you add with the previous hidden state with this multiplication, you add, and you add the bias on this part, and you got G1, which you apply the activation function on all of this, and you provide the information for the next hidden state. Make sense? But this part is also using to do the prediction. Okay? So you can see the RNN like a gate, a simple gate. So the idea of the long short term memory is why we need to improve. The RNN will be good if you have a short sentence like this. Because on this summer school is, we can predict what will happen after. Can you propose me something for the this summer school is? Okay, Okay, time consuming, very good. Okay, but the second sentence is Yoni grew up in Israel. He loves playing with his kids. He's also a great teacher and colleagues. He's fluent in. With the RNN, as he has trouble to get some long dependency, he will not get this information and he will not be able to have a good prediction because the important information is far away. So to solve this, in 1997, I don't remember the author, I will, they proposed the long short-term memory, which is a special case of special gate, and we will see how this LSTM can achieve long-term dependency. So there is a different cell using, and no keep, and to know how it can keep the information and also some discard some memories. So the solution, it will use some different gate, input, forget, and output gate. That's the LSTM. So you have seen the simple gate for the recurrent network, and this it will be an extension. I can see that I'm very slow. I have so many things to say, so I will maybe a bit faster. So the RNN cell, we have seen that there are an hidden state, which I call it HT or AT, and for storing information and making prediction. We have two tasks with the hidden state. And the way of the LSTM is working, we have the hidden state, which is broken, is two states. There are a self state and a hidden state. The self state is called the internal memory, where all the information are stored. And the hidden state is using for completing the output. So it breaks these states in two. So it has been, yes, the author are there. If you click on the link, you get the paper from these two authors we introduced in 1997, a way to overcome the solution of the vanishing gradient problem, even they don't solve completely. So the LSTM, in fact, in this gate is to be more complicated. The cell, the node, in fact, the node is more complex, and there are gates inside. We have seen the simple gates for the RNN, and this we use more gates, more complex. So you can see the gates is like this now. So I will explain a little bit more about this part. Okay. So going was the main idea is that you are there exactly. At each time, the long short-term memory provide a hidden state and a cell state. So the hidden state is HT and the cell state is CT. And the cell state has the power and the ability to store long-term information. This is the main point. And the LSTM can do many things, can erase, write, or read information from the cell. And it can be seen like a gate which are open or closed. So you have the details here in big. So you can see that you have this part of XT, which is the input, and this input take some weight, you multiply with x, you take the information from the previous hidden state, you applied a sigmoid function. The sigmoid function will give you a value between 0 and 1, 0 and 1. So if it's close to 0, the output of this ft in fact will have the ability to forget. So f for forgetting. And this f of t is multiplied by the information from the cell state, the previous cell state. So by multiplying the ft by ct minus 1, he has the ability to forget some part. Okay. And after you have this is called the input gate, this part for the I, and you compute this with compute a new cell content with a 10 function in multiply, and this will have the ability to write new information. So I will just explain the different part of this specific gate. So we say the forget gate with this equation, and it looks all similar. Huh? You can see some weight multiplied by the previous hidden state, some information at the time t and the bias, and you have the sigmoid. Here is the input gate, which is quite similar, and you have the output gate. Mistake here. Which kind of similar equation each time. You can see this. Okay, and this is a way to get the new hidden set and to flow the information. So it's a little bit technical, but I want to show you more stuff on this new cell state. So the main information is that a blink is this gate into 3 gates. We can forget, keep some information, and predict some new information. So, and this has been really exploited in many areas. Put some area. I look like stressed because at 5 minutes, but I will. I think I will use my 10 minutes question. I want to show you some nice stuff. So I will skip a little bit some part here to tell you that the remark that this kind of gates help, in fact, on the also to the optimization problem for the back propagation through the time, because we have uninterrupted gradient flow, and you have a visual explanation, which is, you click here, you have a visual explanation of the back propagation through time for the LSTM and why it's working well. Okay, I will not click on this. There are some extension in 2014. So now you have understood, just, I hope the main idea is that instead to use a simple gate, use LSTM, have inside the gate, there are different, inside the node, sorry, inside the node, there are different gates. And Shaw and al. Propose the GRU for gate recurrent unit, which something a little bit different than the LSTM. And in fact, you can say, oh, I can do a little bit my own architecture inside the node. It's true. Some people try different strategy. So this is another competitor from the LSTM. And the difference between the LSTM and the GRU is there are an input X and hidden state, but there are no cell state. At LSTM, you have a cell state and you have the hidden state. Okay? So this is the main difference. It's very difficult that you see the difference between, and you have the different way how to compute these gates inside the node. I wanted to put too much. So here, if you click on this, you have a comparison between the LSTM and GRU. So it could be also a nice paper for your project. Okay, now I want to go to the encoder decoder because it's used stuff. So it's machine translation, okay? And so you know the machine translation, you have encoder decoder, and we talked about this yesterday, and it's used to do for translation. And maybe I have a question for you. Yes, I wanted to do a question. So just a simple question. Consider the problem to translation to English to French. So for example, what is your name? And in French, you know that is comment tu t'appelles. And I will ask you, is this architecture is good for doing a machine translation? No. Why? There are more English words. Yes, this is a good is the first part because the sentence may be different lengths. Yes, many too many. So this is also the second point. Before translated, you need to see the entire sentence, and after you translate. So a better architecture should be something like, I will not have this very quickly. I will go there, and I will fit this in this one. Okay? This will be the good architecture. Yes, good point. Okay, so this is a way of the encoder decoder. And this have been proposed by Shaw and Tal. I will just expose, and but you have also another version, which is a sequence. You talked about this somebody yesterday, so I say, okay, I would need to go there. Sequence to sequence model proposed by Zuckerberg. And if you click on all of this link, you will have some nice paper on this. So the principle of the Shaw model is that the encoder and the decoder are both GRU. And you know what is a GRU now? It's a specific node with some gates inside. Yes, is also a good point, Jason, is the reason why. So if you look at this paper, this is the specific encoder decoder we use with GRU, and it's pretty powerful. But the Zudeker model, the sequence to sequence model, in fact, is an encoder decoder with a multi-layer, with is exploit Lstm. So Shaw exploit more GRU, and Zuckerberg, I don't pronounce, sorry, Zuckerberg model exploit more the, I would say, the Lstm. And this is like an example of encoder decoder, is why I want to say that the source sentence has to be reversed. Encoder decoder, why I say this? Yes, because the first word I want to, sorry. So in this case, you need to have the sentence reversed, because the first word you want to predict is the first one. So if you put in, okay, you understood. You have understood why is in the different direction. Okay. So if you want to learn something, I eat cheese. Je mange du fromage. Ou je mange le fromage. Okay. Very good point. And I hope somebody will take this for the project. We arrive at the new stuff. Limitation of this model is in nice paper, or they show that the performance of encoder decoder degrades rapidly with the length of the input sentence. So they show this. So what to do better, how to do better. So this is the main drawback. So, and they say also that RNN step is difficult for long sentence. So you need to capture the fact, but you want maybe skip important details. So the good points, you need to read for translation all the sentence, but you might skip some important details. So what we have to do is to put some attention of specific place. So this has been introduced in 2015. Is like a revolution in machine translation. So he applied the attention layer. What is the attention layer? Is a mechanism to give more information for on some input words, and is also using in for image. So is is a kind of layer who will put emphasis of some part of the text or some location of your image. So this attention layer is using by computing some probability of some sequence of some words, and you have a nice survey of this on very recently in 2019 with the attention layer. And I will show you some nice stuff about this. I'm going fast because I have 5 minutes and I want to show you some stuff. So revolution, it was this paper in 2017, is attention is all you need. So you can see a lot of different video on YouTube explain what is this new revolution with the transformer. But in fact, the transformer is, I would say, just is an encoder decoder structure, which is here. So it's like some gates and it's different encoder decoder, and you use the attention layer inside this specific encoder decoder. And apparently is amazing, and it's a revolution, but we still have some drawback. So if you want really to go on this part, I will show you this in 5 minutes, some nice stuff. So understand attention concept. I will click on this, I will open this. So this blog explain to you, so what is the main point of the attention. So for example, in the text, okay, if you want to do some on the image, it's quite clear where you want to put the attention. But on the text, for example, so eating, the combination of eating in green tell you that is low attention, but eating and apple is give a lot of information is high attention. So, and after it explain more how to do this in language processing with the encoder decoder, and you have some explanation here, which is quite nice, and how to compute this kind of score to give some attention score on each word. And you have a kind of matrix like this will give you the attention 2 by 2 for to the combination of words. But before leaving, I have something else. Sorry, is I just saw this today. In fact, is very nice. This one, attention interface. So it is really explain how it's working, and you have some animation also for the attention here. You see click here, but you have the way of how one word is related to the other word and so on. So this is the mechanism of the attention. And before leaving, because I think Sarat will be not happy with me, the transformer. I know that some people like the transformer. So you have here also an illustration of the transformer. And it's quite very nice. And you can see that I still I stole this picture. Je suis étudiant, I am a student, because I went on this one. And so I suggest you, if you like this kind of topic, to go to this post, and they explain very in details how it's working and all, because it's a huge topic, the machine translation. Okay. check, and you have yes, a comprehensive. I put something on PyTorch, which is a tutorial, but it's quite nice. A tutorial in PyTorch is for the sequence to sequence model, because I think it was. I don't remember your name. You asked me yesterday, and yes, and you have also this paper when you compare different machine translation model. I'm sorry to be so long. Take home message. I hope you have learned something. So now is my question, and I think it's almost my last lecture. I really enjoy to get you, but I have also lecture, group lecture with Sarat and Yoni soon. Just before I let Sarat to go, can you give me some people, if you have learned something today, tell me. Disappointed. I'm disappointed. Nobody replied. Everybody left. Yes, transformer. Yes, but transformer. I'm sorry. I wanted to give more on the transformer. Too slow. Ah, yes. RN and Lstm gate perspective. Yes. Okay. I will update a little bit the chapter in a few days, because I saw many typo, in fact, when I did again my slides. Thanks a lot. Still working hard, and you know that I'm still very happy to supervise some project, or if you like machine learning, deep machine learning, plenty of projects. So if you want to go further, you can contact me. Okay, I'll let Sarah drive the next lecture. I'm sorry, Sarah. Can you apologize me?
No problem, Benoit. I think we'll take a couple of minutes break.
Yes.
Yeah, make it 5 minutes, I think.
Okay, so Sarah leads. Thanks a lot for.
Thank you.